Welcome to the massive open online course on Aspen Plus. In this lecture, we are going to discuss about the screening devices and how they are modeled and used in Aspen Plus. Just a small recapitulation of how a screening device works. Screening devices are fabricated from wired mesh. So they look like So this is a typical example of wired mesh having a predefined mesh size. If a particle has a size which is lower than the size of the mesh, then it will pass through that mesh. And if the size of the particle is higher than the mesh size, then it will not pass through the mesh, it will be returned. Or if the mesh is in inclined form, then it will roll over the mesh and go in the other end. So schematically, a screening device looks like this. So if feed, which consists of particles of different sizes, it flows over this mesh, and the mesh is represented by this dotted line, and these are the perforations, that is the mesh. Then some of the particles which are having size less than the mesh size, they will pass through these perforations, and the particles which are having higher size, they will roll over and they will exit from the other end. So this portion of the particles will be termed as overflow, and these particles will be termed as underflow. That means if we take it as a cut size means the limiting size below which the particles will be termed as underflow and over which the particles will be termed as overflow. Now, if there is a second screen below the first one, like this, and its mesh size is lower than the upper one, and if the underflow particles are sent over to this screen, then it will also generate two sets of streams. One is overflow number 2 and underflow number 2. That means this overflow number 2, this set of particles will have a size range which falls between this mesh size, so we call it size 1, and this mesh size, we call it size 2. In other words, this necessarily means that the overflow 2 is the set of particles which fall between two size ranges denoted by S1 and S2, and they are separated and segregated from the rest of the particles. Now, if we have a series of such screens with decreasing order of mesh size, then we will have several of such overflows, and those overflows will be separated and segregated based on certain range of particle sizes. That is the working principle of a screening device. It separates and segregates solid particles as per their size ranges. Now let us go to the Aspen Plus simulation window to learn it better. So this is the Aspen Plus simulation window. Here, if you see the model palette, under the solids tab, you will have the screen over here. So let us take one screen on the simulation window and check what inputs that we have to set in order for it to work. So if we see the material streams, we will find there are three mandatory streams over there. One input stream, one underflow stream, and one overflow stream. And there are optional mid-size streams. As I have already said that if we have several of such screens in the decreasing order of their mesh size, then it is possible for us to get several of overflow materials of different size range. So that is exactly what is done by this screen with optional mid-size. And we can set up to 9 of such optional mid-size. They are given by deck number. So deck number 1, deck number 2, deck number 3, up to deck number 9 we can place. Now let us give the name. Say this is the feed. Obviously it will be solid feed or solid with liquid mixture, but it will be in a slurry form. It will not be homogeneous mixture. And this is underflow. And this is overflow. And we can put some more number of streams just for an example. So let us name them first. Say name is feed. Name it as underflow. Let us name it as over 1. This is over 2. This is over 3. So basically, we are creating 3 decks in a single screening device. So let us open it. And here we can see that we have 3 decks. The deck number 1 is always the overflow number 1. And this one we can say overflow number 2. And this is the overflow number 3. So this is the oversized stream ID that we are putting. And obviously the valid phases we have to place solid only. Okay. Now there are various parameters that we have to set. That is selection function, cut size, sharpness parameter, offset of fines, white beaten, size of screen opening, operating level, operating mode, entrainment specification, entrainment fraction, and entrainment load. So we will learn all of them one by one. Now first, let us see what is selection function. Now if you open this one, you will find there are several selection functions available, namely pleat, Rogers, Molerus, Whiten, Ideal, US Bureau of Mines, and user specified. Obviously, the user specified one is always dependent upon the user who is using this model. If he is having some user specified functions which he has collected from open literature or from his own experimental findings, then only user specified function is useful. Otherwise, for general use, it is always better to use from among the rest of the 6 functions. Now we will learn them one by one. For that, let us go to the selection function and see what actually it is. So these are the selection functions in detail. You can find it in the Aspen Plus help file. Now by definition, a selection function, it is also called the grade efficiency. It is defined as the mass of material within the size class I in the feed that leaves the screen in the core stream. Core stream means the stream which is going overflow, and fine stream means which has passed through the mesh as underflow. So for any screen, there will be a coarse flow and fine flow, which we also call overflow and underflow. And it depends upon the cut size. Now, what is cut size? Cut size is, suppose cut size is 50 millimeter. That means you want any particle below 50 millimeter to pass as underflow of the mesh, and any particle over the size 50 millimeter should be going through overflow or overstream. So anything above the cut size is expected to go as an overflow. Anything below the cut size is expected to go through the underflow. So the selection function is the fraction of material that is going as the overflow as coarse particle. So that is the selection function. Now in general, the selection function is having S-shaped curve, and against the particle size, it will have a value from 0 to 1. Now how this value is calculated, we'll learn now. For that, you go to the different selection functions in screen, and here you will find several definitions. The first definition is DI. Now DI represents the particle size and is calculated as the mean size of the particle size class. So that is the average of lower size and higher size. That means, suppose you have one screen over here, another screen over here, and overflow particle, this is the exit point of those particles. So the upper size of these particles and the lower size of this particle, so the mean of that, the average of that will be called DI. So basically, this should be an average between the cut sizes of this and this. They are basically the lower and upper bounds of the size interval I. And J is the particle size distribution attribute. So suppose the feed is a mixture of various particle flows having their own particle size distributions. Now let us have particle size distributions of this nature, and there the size ranges I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. Here also it is I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. And this is particle size distribution attribute 1. This is particle size distribution attribute 2. This may be RRSB distribution function. This may be log normal distribution function. So the entire flow of particles that fall under this range, collectively they are termed as F11. The entire particle flow that falls under this range is termed as F21. Similarly, this one is F31. This is F41. And this will be F51. Similarly, for this particle size distribution attribute, we will have the entire particles flow over here is called F12. This will be F22. This will be F32. This will be F42. And this will be F52. So the entire flow of feed, they are divided into these subgroups. Okay? And each one of these flows will have their own selection function based on that particular deck. Now let us go back over here. Here you'll find Fij is the flow rate of feed size range I and particle size distribution attribute J. So that is the flow rate I have defined just now. And Si is the selection function, that is the fraction of feed particles in size range I that passes over the screen into the overflow product. Then this particular product, that is Si into summation of all the flow, Fij over j means we collect the flows of that particular size range from all the particle size attributes, sum them up and multiply with that selection function of that particular deck. Okay, so this summation will give us the flow rate of that particular size range. And when we sum that flows over the size range of I, then we will collectively get the entire overflow product. Now let us go into the selection function details. First, let us take the split selection function. You can find the reference over here. It has been published in CIM Bulletin in 1971. If you are interested, you can go to the library or the database where you will find the old journals. You can just dig it up and see how they have derived or how they have developed the model. Here we'll just use it. And this split selection function will have three things to fix. One is A, another is alpha, and two other things, di and dcut, we already know what they are. So at this moment we are interested in A and alpha. Now what are they? A is the offset of fines and alpha, it is the sharpness of separation. To learn offset of fines, let us go over here. It is defined over here that offset of fines is the portion of material which bypasses the separation and goes directly to the coarse product without having a chance to bypass through the screen. Now this regularly happens. The fine particles which are having size less than the mesh size, they are supposed to pass through the mesh and get separated and go through the underflow. But seldom it happens that the particle may have an odd shape which is an hindrance for it to pass through the mesh, or else they may be hidden behind two big coarse particles and they are just carried over from the entry to exit without having a chance to pass through the mesh. And portion of the fines or the fraction of the fines that are carried through bypassing the separation is called offset of fines, and its value may be anything between 0 and 1. In ideal case, the offset of fines will be 0. That means it will begin from here. So that is the ideal case of separation. If offset of fines is 0, then you can take the cut size as median cut size, that is D50. So you can take cut size as D50. For sharpness, just go over there. Now usually the sharpness is defined by Eder, which is the ratio of D25 and D75. This is the sharpness. But actually the sharpness factor may be different, and it is different than the figure that I have shown, that is the ratio of D25 and D75. And the sharpness defines how sharp the selection function will be. If it is too sharp, then the selection function will look like this. Here, sharpness factor is 1. And if sharpness factor deteriorates, then the S-shaped curve will go from this to this to this to this. And in this case, sharpness factor is 0.3. As you decrease the sharpness factor, the shape of selection function will deteriorate. Now the next selection function is Rogers selection function, and you will find it from this literature. And here the function is different, but they have the same set of parameters, that is offset of fines, dcut, and it has a sharpness parameter as well. Now Moleras and Hoffman selection function will also have the same two parameters to be defined, that is offset of fines and cut size. Whiten selection function has an extra parameter. Other than this offset of fines, cut size and sharpness, it also has a parameter called beta. So it has beta and beta star. Now, beta is defined as the initial decrease of overall separation curve at a small particle size. Now, usually we can expect that the separation curve will be of this nature, and if it is having some offset of fines, it should have been this nature, where the offset of fine is over here. But its shape is something like this. It is just like a fish hook. This is the shape of a fish hook. So it is having a fish hook effect. It means that for a certain particle size range, in this case, the range is over here, the overall separation will be decreased. In normal circumstances, the overall separation should not go below the offset of fines. But if you have a fish hook effect, then for certain particle size range, the separation will go below the offset of fines. Now, if beta is 0, that means there is no fish hook effect. But if beta is non-zero, then there will be some fish hook effect, and higher the value of beta, greater the difference between the offset of fines and the minimum in the separation efficiency of the curve. So that is how the beta is defined, and beta star is calculated on the basis of beta. Now, ideal selection function, it uses d cut as the ideal cut point. That means if the upper limit of the size of class I is lower than the cut size, then it takes Si is equal to 1. And if the lower limit of the size of class I is more than the cut size, then it takes the value 0. And if it is in between, if the d cut is between the upper limit and lower limit of the size of the class I, then it uses this particular equation to find out the value of Si. That is ideal selection function. And finally, the US Bureau of Mines selection function. Here you will find the particle diameter, size of screen opening, these two things have to be fixed, and also the separation strength, that is A. And how this separation strength is found? For that, you have to go to the US Bureau of Mines selection function. Here, you will find the separation strength for various ranges of size of screen opening and for various conditions. What are the conditions? You will find two conditions, either dry or wet, and upper or lower. Upper and lower means I have already described that there may be a set of screens. So if the screen in which US Bureau of Mines selection function is used, that is at the upper end, then we will select the US Bureau of Functions on the basis of the value upper. And if the screen in which we are using this US Bureau of Mines selection function is a lower screen, then we will use the phrase lower. And dry and wet, again, if the solid that we are separating, if it is dry solid, then we will call it dry. If it is wet solid, then we'll call wet. For different size of screen opening, these are the values. Suppose the screen opening that we are talking about in meters, it is 0.0095. That means it is 9.5 millimeters. So suppose the screen opening is 9.5 millimeters. Then we choose this particular row. So if the solid is dry and the screen in which we are using this US Bureau of Mines selection function is in upper level, then the value of strength is 8. If it is lower level, you will use 6. And if it is wet solid, then for upper level it will be 8.5 and lower level it will be 6.6. So like that, you use this US Bureau of Mines selection function. And for that, you do not have to choose anything. The system will automatically choose it. Now here, one more thing that you have to remember, that when you are using US Bureau of Mines selection function or user specified selection function, then you have to use the model in which only one deck is there. You cannot use these functions for a multi-deck model. Multi-deck models can be used for other 5 selection functions, but not for them. So that you have to remember. So we know what is selection function, we know what is cut size, sharpness parameter, offset of fines, white and beta, screen opening, operating level, operating mode. Mode means dry or wet. And then these are the entrainment specification. Now let us learn what is entrainment specification. Now entrainment specification defines the distribution of fluid phase in the overflow and underflow. That means if we have some fluid along with the solid product, then the screen will divide the fluid based on our specification in the overflow or in the underflow. Now, the 6 possibilities are there. Suppose we take the coarse frac first. What is coarse frac? This is specified fluid fraction in core stream. Now, if we set a value of FF coarse, that means what is the fraction of mass, total mass that is going into the coarse product, which is fluid. Suppose the total mass in the coarse product is 1000 kg per second. And we have set this value as 0.3. Then out of 1000 kg, 300 kg will be fluid and 700 kg will be solid. Okay. Similarly, fine frac means the total flow that is going as the underflow. What is the fraction of that flow is fluid. That is the FF fine that we have to specify. Now, suppose 1200 kg of material that is flowing as underflow, and if we set fine frac as 0.5, that means 600 kg per second will be fluid and 600 kg will be solid. Then coarse load, that is specified fluid loading in the coarse stream. This is the ratio of mass of fluid in the coarse product and mass of solid in the coarse product. So that is coarse load. Fines load will be defined the same manner. Coarse split means what is the fraction of inlet feed of fluid that will pass through the coarse flow. That is the coarse split. Fine split is defined accordingly, and equal split means it will be in the same proportion as the solid phase. And the equations are given over here. You can study yourself. So this is how you specify the entrainment parameters. Now let us solve an example problem to understand it better. For that we go to the example problem.